Jungle.
Second quarter, electronic structure of matter.
Subtopics: atomic theory. Timeline: describe an atom quantum mechanical model. Sublevels and capacity of the first four main energy level Aufbau principle. Pauli's exclusion principle.
Atomic theory timeline. John Dalton, British chemist and physicist, proposed the solid sphere model in the early 19th century, shifted from philosophical ideas to scientific theory. First atomic model based on experimental evidence and quantitative observations, paved the way for the development of modern atomic theories. Solid sphere model. Atomic theory. According to this theory, atoms are tiny balls that can't be broken and are all made of the same material. This theory helped explain how different chemicals mix together and what makes them different. Limitations. Couldn't explain differences in atomic mass within an element, isotopes. Didn't account for the presence of subatomic particles like protons, neutrons, and electrons. Couldn't explain the behavior of atoms in chemical reactions. J.J. Thomson, English physicist known for his work on the nature of electrons, proposed the plum pudding model in the late 19th century. Discovered electrons as distinct particles. Shifted understanding from indivisible atom to subatomic particles. Paved the way for further exploration of atomic structure. Plum pudding model. According to this theory, atoms are like plum pudding with tiny positive charges scattered throughout a cloud of negative electrons. This theory helped explain why atoms have a neutral charge overall and why they emit light when they collide with each other. Limitations. Couldn't explain why electrons didn't collapse into the positive sphere. Failed to predict the distribution and arrangement of electrons. Lacked explanation for the nucleus and its positive charge. Ernest Rutherford, New Zealand-born physicist known for his contributions to nuclear physics, introduced the nuclear model in the early 20th century. First model to propose a central massive nucleus. Explained the behavior of positively charged alpha particles in the gold foil experiment. Laid the groundwork for understanding atomic structure and radioactivity. Nuclear model. According to this theory, atoms have a nucleus with a positive charge and most of the mass, surrounded by electrons that orbit like planets. It explains why particles can pass through or bounce off atoms, and is the basis of our current understanding of atomic structure. Limitations. Didn't explain the stability of the nucleus against electrostatic repulsion. Lacked details about electron orbits and energy levels. Didn't incorporate the principles of quantum mechanics. Niels Bohr, Danish physicist known for his pioneering work in atomic structure, proposed the planetary model in the early 20th century. Explained atomic spectra with precision. Introduced the concept of quantized energy levels. Bridged classical physics with emerging quantum mechanics. Niels Bohr. Each orbit was given a number called the quantum number. Bohr orbits are like steps of a ladder, each at a specific distance from the nucleus and each at a specific energy. Niels Bohr. The lowest allowable energy state of an atom is called its ground state. When an atom gains energy, it is in an excited state. This is an illustration of the Bohr model with label. Planetary model. According to this theory, electrons orbit the nucleus of an atom in specific energy levels or shells. This theory helped explain why atoms emit light and why they absorb certain colors of light. It also helped explain the stability of atoms and why they don't fall apart. Limitations. Limited to explaining the hydrogen atom. Couldn't account for the behavior of multi-electron atoms. Didn't incorporate the wave-like nature of electrons. Erwin Schrödinger, Austrian physicist renowned for his contributions to quantum mechanics, proposed the quantum model in the 1920s. Quantum mechanics provides a comprehensive understanding of electron behavior. Schrödinger's model successfully explains multi-electron atoms. Quantum mechanics is the foundation of modern atomic theory. Quantum model. According to this theory, electrons exist as a probable wave-like pattern around the nucleus, not in a specific orbit. It explains why electrons act like particles and waves, and is the foundation of our understanding of atomic structure and widely used in modern physics. Limitations: mathematical complexity of the model. Requires advanced mathematics to calculate electron probabilities. Doesn't provide a simple visual representation of atomic structure. Quantum model. Louis de Broglie, 1892–1987, hypothesized that particles, including electrons, could also have wave-like behaviors. Electrons do not behave like particles flying through space. We cannot, in general, describe their exact paths. Schrödinger treated electrons as waves in a model called the quantum mechanical model of the atom. Schrödinger's equation applied equally well to elements other than hydrogen, unlike Bohr's model. And the quantum mechanical model. A number and a letter specify an orbital. The lowest energy orbital is called the 1s orbital. It is specified by the number 1 and the letter s. The number is called the principal quantum number, n, and it indicates the relative size and energy of atomic orbitals. N specifies the atom's major energy levels, called the principal energy levels. How quantum mechanical model describes the energies and positions of the electron. To describe the atomic orbitals and to label the electrons that reside in them, a set of quantum numbers has to be identified. The principal quantum numbers n designate the main energy level where the electrons are located. The main energy level is also called a shell, and its n value describes the most probable distance of the electron from the nucleus. The greater the value of n, the farther the electron is from the nucleus. The secondary quantum number gives the total number of sublevels or subshells possible in a given main energy level or shell. It also describes the type of orbital where the electron is. This table shows the allowable number of electrons in each main energy level and orbital of the atom. This table shows the hydrogen's first 4 principal energy levels. In an atom, electrons occupy the orbitals in the order of increasing energy. The lowest energy levels are filled up before going to the next energy level. This order is known as the Aufbau principle. Hund's rule states that, when assigning electrons to orbitals, an electron first seeks to fill all the orbitals with similar energy. Pauli's exclusion principle states, no 2 electrons in an atom can have an identical set of 4 quantum numbers. The mnemonic device presented below can guide us to determine the order of increasing energy of the orbitals. Therefore, quantum mechanical model of an atom shows how the electrons surround the atom in increasing order. Energy levels are the fixed distances from the nucleus where you can find the electrons of an atom. The mnemonic device guides us in arranging the order of increasing energy of the orbitals. Valence electrons are the electrons occupying the highest energy level.